Hello, this is Dr. V.C. Sontage, Assistant Professor in the Department of Mechanical Engineering, St. Vincent Pallotti College of Engineering and Technology, Nagpur. I am going to teach the course Heat Transfer. The objectives of this video lecture are: first, I will introduce laws of heat transfer. Then, we will be talking about the applications of laws of heat transfer, and last we will be discussing in great detail about the law of heat conduction. Laws of heat transfer. There are basically three laws of heat transfer, and these three laws of heat transfer correspond to three modes of heat transfer: conduction, convection and radiation. So the very first law of heat transfer is law of conduction. It is also called as Fourier's law of heat conduction. The second law is the law of convection. It is also called as law of Newton's law of cooling. And the third law is law of radiation. It is also called as Stephen Boltzmann law of radiation. So let us first discuss law of conduction, also called as Fourier's law of heat conduction. Fourier's law of heat conduction. This fundamental law of heat conduction was first proposed by French scientist Joseph B. Fourier in 1822. This law is an empirical law, means this law cannot be derived from the first principle, and it is purely based upon the observations and experimentations. Statement of this law. The Fourier's law of heat conduction states that the rate of heat transfer by conduction through a solid material is directly proportional to the area normal to the heat flow and the temperature gradient, and inversely proportional to the thickness of the solid material. This thickness is also called as the length of the path of the heat flow. Assumptions. While dealing with the Fourier's law of heat conduction or applying it to particular case to calculate heat transfer rate by conduction, following assumptions must kept in mind. Assumption number 1. The heat transfer or heat flow takes place under steady state conditions. It means the rate of heat transfer remains constant with respect to time, and the temperature between two fixed points within the body does not change with respect to time as well. It means temperature is not the function of time, it is independent of time. Assumption number 2. The heat transfer takes place only in one direction. That is, temperature is a function of only one space coordinate. The temperature may vary either in x, y or z direction only. Number 3, the temperature gradient is constant and the temperature profile is linear. Number 4, the solid material through which the heat transfer is taking place by conduction does not generate any heat inside it on its own. That is, there is no internal generation within the body itself. And number 5, The material is homogeneous and isotropic through which heat is being conducted. As far as homogeneous material is concerned, its properties are same and constant throughout its chemical composition. For example, its property like density, viscosity, thermal conductivity, electrical conductivity are constant throughout its throughout its composition. Isotropic material means its properties do not vary with respect to the direction. If I consider isotropic material, its properties are same whether you move in x direction or in y direction or in the z direction within the material itself. So these assumptions are basically, you can say, the outline of the area, the outline of the study in which Fourier's law of heat conduction will be applied to calculate heat transfer rate by conduction. In order to understand the Fourier's law of heat conduction, let us consider a solid slab having its left phase at temperature T1, right phase at temperature T2. As T1 is greater than T2, so by virtue of this temperature difference and from the second law of thermodynamics, heat transfer will take place from left phase to the right phase at a rate of Q, say. Let the thickness of this slab is L. This L is also called as length of path of heat flow because heat will be flowing from left phase to the right phase by covering this much distance L. Hence it is called as length of path of heat flow. Let's say D is the depth of this slab material and H is its height. Hence from Fourier's law of heat conduction, mathematically, the rate of heat conducted through this solid material, Q is directly proportional to the area A, Q is directly proportional to the temperature difference dt, and Q is directly proportional to 1 by L, where the A is area normal to heat flow. In the present case, it is D multiplied by H in meter square. dt is the temperature gradient across the left and right faces. It is also given as T1 minus T2, and L is thickness or length of the path of the heat flow measured in meter. On combining all these three equations, I will get this one equation for heat transfer rate Q is directly proportional to A into dt by L. When sign of proportionality is removed, we have to introduce one constant of proportionality. So it will give me this equation. Q is equal to minus K into A into dt by L, where K is a constant of proportionality and is known as thermal conductivity of the material through which heat is being conducted. Its unit is taken as watt per meter Kelvin or watt per meter degree Celsius. So we have this mathematical form of Fourier's law of heat conduction to calculate heat transfer rate. While heat is being transferred from left to right phase, temperature of the slab varies, and it varies linearly, and it is called as temperature profile. Why it is linear? we will be discussing in subsequent lectures. Now, in the heat transfer rate equation of Fourier's law of heat conduction, A is taken as area normal to heat flow. Now, mind well, this area is neither a cross-sectional area nor surface area. It is an area normal to heat transfer. So let us understand what do you mean by the area normal to heat transfer by taking these two cases. In case 1, the slab is oriented such that this face is perpendicular or normal to the heat transfer. Let's say the depth of this slab material is D, height is H, and thickness is L. In order to calculate this heat transfer rate Q by Fourier's law, the area normal to heat transfer will be H into D, because this is the area which is normal to this heat flow. So H by D will be the area normal to heat transfer. To calculate heat transfer rate. Let us consider case 2. Let us consider the same body, but now it is oriented in such a way that this face is normal to heat transfer. Under this configuration, let's say the depth of the slab is L, its length of path of heat flow or thickness is changed to D, and height is H. Under such condition, the area normal to heat transfer will be H into L, because this area is normal to heat transfer. So this is very important concept while dealing with the Fourier's law of heat conduction. Many times students may get confused what the A is actually, whether it is cross-sectional area or surface area. So please keep in mind this discussion while taking or while calculating area normal to heat transfer. Now, in the mathematical form of Fourier's law of heat conduction, given by the equation Q is equal to minus K A dt by L, the dt by L is also called as temperature gradient, and its unit is taken as degree Celsius per meter or Kelvin per meter, and it is given as difference of temperatures T1 minus T2 over L, and generally it is negative. It is also called as the slope of temperature curve on temperature distance diagram. The temperature gradient is generally negative because heat transfer takes place from T1 to T2. Sorry, it is T2 minus T1, and T2 is less than T1, so this dt by dl value comes out negative. Now in the above equation, the negative sign is introduced arbitrarily to make the heat transfer rate positive, as temperature gradient is negative. So the temperature gradient will introduce one minus sign, and it will be nullify this minus to make this heat transfer rate positive. Negative sign in the above equation also signifies that heat transfer takes place in the direction of decreasing temperature. Also, heat transfer per unit area is called as a heat flux, and it is given as heat transfer rate divided by area. So Fourier's law of heat conduction will calculate heat flux is equal to minus K dt by L. Let me correct this. So heat flux will be minus K dt by L watt per meter square. Now some essential and salient features of Fourier's law of heat conduction. Number one, this law is applicable to all matters, maybe solid, liquid, or gases. Fourier's law of heat conduction is purely based upon experimental observations and evidences, and hence it cannot be derived by first principle, and that's why it is called as an empirical law. Fourier's law is a vector expression of heat transfer rate. It means it gives the direction of heat transfer rate as well. According to the Fourier's law of heat conduction, heat transfer takes place in the direction of decreasing temperature. And fourth, Fourier's law of heat conduction defines a property of the material through which heat is being conducted. And this property is called as thermal conductivity. So following is the summary of this video lecture. I hope we have come across the different laws of heat transfer. Then we have discussed the Fourier's law of heat conduction in detail. Under this Fourier's law of heat conduction, we have come across its statement, its mathematical form to calculate heat transfer rate by conduction, then different assumptions and its applicability. And we have come across a new property of the material called as thermal conductivity. With this, I come to an end of this lecture. Thank you for patient hearing, listening, and happy learning.